All right, so maybe we'll make a start. So thank you everybody for coming. Today we have Beau from Arm giving us a talk about debugging and optimization using Arm Forge. Yeah, so take it away.
Okay, thank you. So I'm just going to go through a few PowerPoint slides to give an overview of our tools and then spend the better part of our hour going over DDT. And then we have a session scheduled next week, which will focus on our performance tools, performance reports, and map. So just want to make sure, so I'm advancing the slides here. Is that working good?
Yep.
All good.
All good. Okay, so Forge is the integration of our debugger, DDT, our source code profiler map, and our application profiler performance reports. Our tools are cross-platform, so we work on obviously ARM architecture, x86, and we support NVIDIA GPUs. Both architectural-wise and kind of user interface-wise, the tools are very focused on traditional HPC, particular SPMD type codes, so codes that typically might use MPI and or OpenMP. Very easy to use, focused on end user ease of use. Just some highlights in DDT, and I'll be going through a demonstration of all these today. Scalable print statements, its ability to output values from the debugger without modifying the code or rerunning. Watch points, the ability to halt execution dependent upon the value of an expression. Static analysis, so before you even run the code, we do some analysis of potential problems like using variables that have not been initialized, failing to free memory, those type of issues that can be detected without execution. Memory debugging, the ability to detect reading or writing outside of an array. Heap corruption, memory allocation errors, those type of problems. Performance tools. So before talking about the performance tools of what they are, how they work, and giving the overview, I'd just like to present the performance roadmap, and I'll go into this a little more detail next week when we're talking about performance. But essentially really want to highlight the importance of following the correct methodology when you're optimizing. Is number one is make sure that the program's correct. It's easy to make it fast if it doesn't have to be correct. Then focusing on potential biggest problems, in particular I/O and MPI communication. You can have issues that are orders of magnitude large in those areas, and if you're focusing on things like memory issues or vectorization, which are important when you get to that point of the performance roadmap, it can be a big challenge. So using a methodology, following the roadmap, and we'll go into that a little bit more detail. So I saw a comment pop by really quick on the chat there, but I didn't get the full context. Do we have a question?
Yeah, it's what languages are supported by the static analysis?
That's a great question. So a couple parts of that is our tools support C, C++, Fortran, and Python. For the static analysis, we don't yet support Python, so we just support C, C++, and most flavors of Fortran. So performance reports, this is kind of our first pass performance tool. This is just a one-page summary of your application's performance. So a very high-level view, a really good way to see kind of high-level issues, for example, I/O or communication balance that I mentioned in the performance roadmap. So kind of a quick snapshot as a starting point for optimization. Very low overhead, typically much less than 5% runtime overhead. Also, you do not need symbols. Unlike source code profiling, where you typically need to add in a -G to your optimized code, with performance reports, you do not. You can run a typical fully optimized release build. Although on that subject, we've been encouraging customers to move to release builds, including symbols, in that at this point, it's typically very low overhead. And when you're running at larger scale and something does crash, if you have symbols, there's a chance that you can bring up a core file or attach to a blocked program and figure something out with the debugger, whereas if you don't have symbols, probably not much of a chance of that. So just some highlights of MAP. This is our source code profiler. Very visually oriented, and next week we'll be going in depth of how MAP works and looks and how to use it. But the ability to find memory usage, kind of peak memory usage. So for situations where you are leaking memory, it's a nice way to track that down through profiling. MPI imbalance. As you mentioned in the performance roadmap, one of the first milestones on the performance roadmap, making sure that you don't have blocking issues in MPI or IO. OpenMP, a lot of capabilities for analyzing OpenMP and making sure that you're good at getting good balance across threads in a process. Memory patterns, a lot of tools for looking at memory access. And then, of course, as we get farther down the roadmap in the final steps, especially on modern architectures, getting good vectorization. Python, just like to highlight this, is a fairly new capability in our tools for both profiling and debugging is support for Python. I really like to highlight that it's for what I like to call HPC Python, something that might typically use MPI for Pi or another SPMD oriented tool. Obviously, Python's used for a lot of data munging type of activities, and that's not exactly what we're focused on, but we're seeing a lot of growth in kind of the MPI for Pi type of applications. And if you're doing that type of work, support in Python works great. And just some follow-up material, some of it relevant for what we're going to be talking about in DDT, some of it for MAP. Apologize, I had customized this for work at Argonne last week, but I've seen the web specific stuff on Archer, so hopefully we can make an addendum to this that references the relevant Archer pages. Okay, so today we're focused on DDT, so I'm going to start up with a relatively simple toy code that's using 4 MPI processes. Now, one thing I want to highlight is I'm running in the virtual machine, and the preferred method is that you install a client on your desktop, and we have clients for Windows, Macintosh, and Linux, and then you connect to your machine through remote connect and submit the job from your batch file on the cluster. So you go into your existing batch file, prefix the existing MPI run, app run type of launcher with DDT -- connect, and it will come up and connect with this. And we don't have time to go through that whole process in an hour, but I know that your site's set up with that. So if you have questions with that, please follow up. But I'm kind of new to your site, and I know that you support it, and just wanted to mention that's the preferred way to run if you're new. Okay, so the startup dialog.
Beau, sorry, just before we continue, we had another question come in. Does support for Python include extension modules written in, for example, C or C++ or Python?
Yeah, certainly it does. And in all fairness, that's probably the most common methods is linking in with something like NumPy or your own compiled code. And there's a couple little subtleties of it of when you step into the compiled part of the code. If it's not your code, you're going to need symbols to be able to do that. So with NumPy, you need to do a non-default build to get the symbols or whatever the toolkit is. And also to step from the Python code into the compiled C or Fortran, you either want to set a breakpoint in the compiled code, bring up the source, set a breakpoint, or just halt at the statement before entering it. But yes, indeed, that's fully supported, and that's probably the preferred method. And I believe in the follow-up materials that I had in my slide, I have a reference to a blog entry, or actually it's a webinar that one of my colleagues did on using NumPy and going through that process in a lot more detail.
Okay, great, thanks.
Okay, so make believe I connected with my remote client to your cluster. You submitted your job, and it will use SSH to connect back to DDT and then start up. So let me go through the user interface a little bit. At the top, we have components for running processes, setting breakpoints, stepping into blocks, manipulating the stack frame. A relatively new one, assembly mode. Kind of interesting. We're seeing, I think in recent history, there's a lot more work of moving codes onto different platforms. I'm obviously being an employee of ARM. I'm involved with going between ARM and x86 platforms, and being able to look at assembly code is once again interesting. For a long time when we were completing on x86, not quite so. On the left-hand side, kind of a navigator, kind of a project navigator, like an IDE might have, something like Visual Studio or some of the Eclipse plugins, where you can search across your project, manipulate what you're looking at in the project. Then to the right, source code view, the little roadside kind of warning signs that I mentioned for static analysis. You hover over those and it'll give some information about potential issues that it found from static analysis. Also, you can directly edit, build, and rerun within the source code view. So if you go to edit file and set up how you build your program, and we're not intended to be a complete make type system, but essentially just call the make file or whatever build tool you're using to run your program. You can rebuild the executable, and DDT will dispatch a new executable to each of the compute nodes. So not intended to be a complete development environment, but for situations where you're running and you have a kind of quick and dirty idea of what is wrong with the program, and it might take a while to resubmit your job, get your turn in the queue. It's a very efficient way to do quick edit rebuild cycles from within the tool. Also integrates with source code control tools. And I do not have a Git repo with this, but if you had a repo that you were using with it, it would show next to each line of code what the provenance of that code is from the repos, with the idea that new bugs typically appear near recently added code. Kind of makes sense. Now to the right of the source code view, view of variables. So let me just step along a few lines here to instantiate a few things. Okay, so we can navigate, we hover over variables and get some information about the type and the definition and the value that's been instantiated. If we click on the variable, we can drill down to sub-elements. So particularly with structures, it's a nice way to drill down into the structure and see subcomponents of the structures. We can also expand arrays, but we'll go into another way to look at arrays a little bit later. Now to the right of the variable, it's a little plot, sparkline plot, where it shows the kind of like the shape. I prefer to call it the shape, not the value, because at large scale we can't show all the values of the variable across all the processes. So once again, in terms of kind of scalability with large process counts, it's an easy way to see that the variable kind of has the a priori shape that we expect. So for example, with my rank, we're going to typically expect that to be this monotonically increasing curve from 0 to n-1. And then if we click on that, we can bring up details on the variable, see the actual values across the processes, some statistics on the variable across the processes. So a very powerful way to see that a given variable has the expected values across processes, or if something stands out, it would be like a simple spike within that sparkline plot. We can also export it into a CSV file or an HDF file. Okay, the bottom we have various tabs, which are kind of the heart of the debugger for operations of manipulating and controlling execution, controlling output. One I like to start with is the logbook. one thing we've been trying to really promote for quite a few years now is use a little bit more methodology when debugging. I think debugging is unique compared to a lot of development type of endeavors in that nobody starts in for the search of a bug and says, boy, I'm going to spend a few days finding this bug. It's our natural inclinations always say, boy, I have a good idea what this is, and jump right in. And that's often the case, and that's great. But for situations where the pursuit ends up being a big challenge and with a lot of issues, if we're a little more methodical about it and kind of approach it as a scientific experiment, and in fact, I think one of my follow-ups in the slides is a presentation I did at GTC specifically on using methodology in debugging, and I go into that a little bit more depth. But at highlight, just want to point out the idea of, even if it's just a little bit of approach where when you dive in, kind of approach it as a hypothesis, and make a hypothesis of what your problem is, and use the logbook. The logbook keeps track of your notes, the execution state of the program as you go along. When you get into the situation that the bug turns out to be much more challenging than you think, and you're days into it, if you've systematically approached the problem, it is usually much more fruitful. So not too much depth on that, but that's a whole training session we go into, but I just want to kind of highlight the logbook as a tool for supporting better methodology debugging. Breakpoints. So breakpoints are the ability to halt execution by location. And for breakpoints and most of the features within DDT, I really encourage using the user interface components, and that things are pretty self-documenting of how to do things and what is available. So for breakpoint, go to the breakpoint tab, right-click within the body of the tab, and bring up the dialog. And from the dialog, it's kind of a nice reminder of how to use the breakpoint and what can be done with the break. So we can halt execution at a line location, at a function entry point, for a specific process, thread, or process group. So I'm not using any OpenMP in this program, so no threading. We can also control the iterator space, so every nth pass or only a certain number of iterations. And probably one of the most powerful actually is on a conditional. I think there's a lot of cases where you'll have a bug that does not occur until after iterator I, j, k are within whatever iterator space. And this is a really powerful way to focus that. And once again, in the spirit of methodology, of if you really give some thought of what is the error space of your problem, trying to focus the search has a few benefits in that it's a lot less data to go through, and of course it's a little less overhead on the debugger when you run. Okay, I'm going to add a breakpoint for all 4 processes to halt at line 108. Hit play, and you can see that all 4 processes halted at that location. Also, another way to see that is from the location of the blue line. So if I hover over where the line is blue, it'll show which processes are located on that line. So for codes that are a little more complicated or long running, the more typical scenario is you're going to have different processes on different locations when you halt all of the processes. And looking for the blue line in the various contexts is a good way to see that. And we can hover over that, and also by manipulating these squares at the top, we can change the context that we're looking at. So for example, selecting block numbered 1, I can look over in the locals tab and see that I'm now looking at my rank 1, and the blue line confirms that rank 1 is also on that. But we're going to go back to process 0. Once again, go back to the locals tab, verify, yep, my rank is 0, so we're back looking at process 0. Okay, trace points. So I mentioned in the overview the ability to output values from the debugger without modifying the code, without having to rerun. We call it trace points. So once again, let's use the dialog. It's kind of an illustration of what to do, what we can do, and how to do it. So go to the Trace Points tab, bring up the dialog. Once again, we can do this by line location, function entry point for a specific process or process group. Also have the ability to limit the iterator space and have a conditional, just like we do in the breakpoints, and then an area to output the values that we want to output. And I'm going to output X and Y. They're just kind of loop control variables in this loop. Process group. One I don't think I mentioned in breakpoints strictly is process groups. You can define, if you know the problem is limited to a subset of processes, you can define a group that includes only those processes. So once again, a powerful way to focus your search, limit the domain that you're debugging over. Also in something like coupled codes, I kind of came from the WRF climate type world, and there was often cases where you'd be looking at different kind of coupled model components, and this is a way to focus your search in those situations. Okay, I'm going to output X and Y. Maybe just do it every other pass. I'm just trying to get a look at what the iterator space looks like. Okay, I'm going to select the next line past that block that is populating that tables array. Right click and run all processes. Another just a usability tip within DDT is we saw how in the variables view hovering over items gives you interesting information depending on the context. Might be what the definition looks like, what the value is if it's been instantiated. Another usability tip is right clicking on a token will bring up a menu of things that are typically of interest in the given context. So I click on a line and has some accelerators of things of interest. I'm going to run all processes to the selected line. And we can see the blocks at the top changing color to represent the execution state. Now they're all back to paused. All right, so let's go to the trace point output tab. So this is the output from that iteration with the output in a similar form as we have in the variables view, where it uses the sparkline plot to show the shape of the variable across all of those processes. And then it also gives the actual range of that value at the given iteration step. So really powerful alternative to print statements in a couple dimensions. It's a lot more scalable, but in a certain way almost more important is a challenge with print statements is always that you're changing the determinism of the program, and especially for bugs that are related to memory issues, that can really wreak havoc of the bug will appear to migrate or even go away. And as you run at more processes, that changing of the determinism by using print statements becomes even more of a problem. So trace point's a nice alternative to that approach, and also doesn't require modifying the code, which can make for a much slower process in HPC. Okay, breakpoints, halting by location, trace points, outputting at a location, watch points, the ability to halt dependent upon the value of an expression. So I still have the value here. So this also highlights one other aspect in DDT is when you're setting up your experiment and putting in breakpoints and watch points, you can turn them on and off between sessions. So this one, I set this up in a previous session, and by default, it was still defined when I brought it up today. But I can turn it on, turn it off, add other ones, turn those on and off. So when you get into the situation of a complex debugging session and you're doing a lot of iterations and you're making experiments to support your hypotheses of what you put in your logbook, what the problem is, it's a versatile way to set up a lot of different experiments. So let me just bring up the watch points that I've already defined. So in this case, right click on it and select edit. And once again, we can do it for a specific process group. Since this is related to an expression, there's not options for the iterator space because it doesn't have that in this context. Define the expression. So I'm just going to enter in the name of a defined variable in this scope being watched. And we can set the watch point to halt execution either for read or write or both. I'm going to say halt execution for both. And then select play to continue execution of all processes. And once again, the dialogues shows us that all 4 processes have halted on the next statement after being watched is assigned a new value, and shows the new and old value for it. So really important for cases where you get to a location in your code, the state is not what you expect, but you really don't have any idea of where the state inappropriately changed, where things got messed up. It could be way upstream in your own code, it could be in other modules, other components. Watch points are really a powerful tool to track down those type of locations. One thing I like to point out, especially for sites with big systems, is watch points in most hardware can be supported by the hardware, and we also support them in software. And when you set that, if you're using a lot of watch points, you want to kind of just be attentive of how it's implemented. Once we run out of hardware supported watch points, we will do them in software, and that can be quite expensive. So depending on your machine, there's a finite and usually fairly small number that can be supported in hardware. So if you're making heavy use of those, do just be attentive of if it's being done in hardware or software. Okay, so evaluate window. So we looked at the variables view of how we can view variables, atomic variables, through the locals tab, kind of a read-only view. We can also edit. If we drag the variable to the evaluate window, we can modify it in various ways. We casting pointers, so for example, changing how pointers are referenced, changing the type of pointers. You could actually change the execution within the debugger. In this case, I'm just going to actually edit a value. So let's say change my rank for process 1 to value 22. And once again, we can see in the sparkline how it changed. So it stands out right away that it's no longer that monotonically increasing line. We can bring back up the compare across processes window and get the actual details. So once again, it's a powerful way if you have a hypothesis of, boy, if XYZ just contains these values, I think it would correct the program. It's a way to interactively to test your hypotheses. And once again, really encourage you to kind of use the logbook, keep track of your experiment of why you think that's the case, and if it was not the case, what your conclusion was. So for your next debugging iteration, it gives you kind of a framework to continue. Okay, so kind of memory debugging and memory analysis tools. I think it's really more than memory debugging. I used to always call it memory debugging. It's really a little more involved with that. It's often just understanding memory. And a big part on HPC is making sure you're making best use of your resources. So a lot of times the exercise of seeing that you're using, you know, high threshold of memory within a node or within a given process for the how that node is configured and set up, which is really not debugging per se. It's really almost more of a performance optimization exercise, but the debugger can really help those tasks of understanding memory usage in a given application and making best uses of your resources. So there's a couple tools. Oh, I ran without memory bugging, so let's start over. So by default, the memory tools are not turned on. So memory debugging, so let's click memory debugging. Quickly just go over details. These are kind of the defaults that I recommend that will catch a very high percentage of memory related issues with a pretty modest amount of overhead. I don't believe these are the defaults in most sites, but just in general across a lot of different systems, just subjectively, this is what I found does a pretty good job with minimal overhead. The heap debugging, essentially this is a bunch of flags for catching heap related issues, corruption, overwriting, things like that. I suggest starting with balanced. As I said, just subjectively found that catches a lot of problems, not a lot of overhead. Guard pages has the ability to detect if you've read or written outside of an array that's defined. And then just a little bit more heap checking options. Once again, just subjectively, these are ones that I found are fairly low overhead. If you're running really rich C++ code with a lot of runtime, creation of objects, that type of overhead can get a little bit higher. Also, just one other comment on this is a couple things. Intel compiler in particular has flags for detecting if you've read or written outside of an array, and they do an extremely good job, but it's much more overhead than in the debugger. So if you're a fan of that capability, I suggest starting with the debugger, and if you don't find what you're looking for, the Intel compiler in particular's capabilities for that are great, but you might be able to find your problem with a lot less overhead. Also, heap issues. Another tool that I'm a big supporter of is Valgrind. Also does an excellent job, but you can often find a lot of those type of issues within the debugger with far less overhead. Okay, so now let's actually have a look. Okay, so two main memory-related tools within DDT is memory stats, memory usage. We go to tools, memory stats, memory usage. I like to start with memory stats, having a look at that first for a couple reasons. It's more of a high-level view of how memory has been allocated, what's been free, call counts, that type of issue. So it's just sensibly a kind of a first high-level look to see if anything's standing out. So at this point, this program doesn't have any really memory anomalies. All the processes have allocated and free the same amount. Also, this information is stored in the main daemon for DDT on the login node. So it does not need to go out to the compute nodes and gather in for any information. So it's no matter what scale you're running at, this dialog will come up very quickly. So the second step then is to bring up memory usage. So at this point, it's going to go out to each of the compute nodes, communicate with the DDT daemon on each of the compute nodes to query the kernel on the compute node to get low-level information about the actual functions in processes that have been making allocations, freeze, what the memory behavior is. And so we can see that with the legend, it shows a legend of what the processes are, and we can click on them. In this case, these are all system things, so not particularly interesting, and see where the actual locations are made and navigate back to to the source code that are making the allocations. So a great way to get a better understanding of where memory is being used, how it's being used, how much memory is being used. And next week we will go through in MAP of using the memory profiling capability to see places where there's anomalous changes in memory usage as kind of a debugging technique, almost more than a profiling technique, to spot memory leaks and memory issues like that. And when we do that, we'll be coming back to this tool with the information that we learn in the profiling process. Okay, so one other item in here I kind of missed on the first pass, so we'll go over it now, is how to look at data in a more visual way than we see in the locals tab. So I'm going to run all processes past that block that was populating the tables array. And now if we click on tables, let's again use the right-click menu to see some things that might be of interest. In this case, I want to select tables, view array. So it brings up a dialog, and it detected that this was a 12 by 12 array. And by default, we can bring it up in a spreadsheet. We can also kind of limit the domain that we're looking at. To kind of limit the domain of what we're looking at. And we can put simple expressions in the only show if field. Most typically are is inf, is nan, not is inf, not is nan. That's a really useful way for cases where you have those kind of values in your data and you're trying to figure out how they came in, is using the only show if dialog or field in this dialog with the is inf, is nan built-ins. Similar to the locals tab, get statistics across the variable, and also export it as a CSV file or an HDF file. And we've seen some really creative usage of that capability of like exporting it to an HDF file. So say you have a variable at various versions of your program or various check-in periods, and trying to figure out when a problem came into the build. Seen folks export this as an HDF file and use some of the Python tools to visualize elements of a variable across versions and historical epochs of a program. Kind of fun stuff. Okay, so great for seeing in tabular form. For bigger data sets, bring it up as a picture. So especially for large components, a very easy way to see that the data has the a priori shape that you expect. And I seem to always be reminded here of GPUs, in that this capability is particularly powerful with GPUs, where you need to stage the data on the host, transfer the data to the GPU, do your work, get the data back to the host. There's a lot of steps where things can go wrong, and this is a great tool to track that down. And I apologize, I don't know the setup on your side really well if you're using GPUs a lot, but if you are on CUDA GPUs, everything that I've shown today works the same on CUDA as it does on a host. So breakpoints, watch points, in-device code, that all looks and feels and works the same. And the Ray viewer also works the same. So when you're on the device, you can bring up device memory variables and look at it the same way that we hear on the host. Okay, so that's the bulk of interactive stuff that I wanted to show with DDT today. And I'm going to move on to what I call offline debugging, which is essentially just using the debugger without the user interface. And there's a few steps involved in that. But maybe before we do that, just kind of proactively ask, are there any questions on what we've seen so far? Okay, so let's do a little bit on offline debugging. So I said offline debugging is the ability to run the debugger without the user interface. So for cases where it's a very large job and you might not be able to get a reservation, or it takes a while for you to get your turn in the batch system. Also for cases where
Sorry, yeah, we do have a question. It says, I don't understand what it would mean to change the type of a pointer while running a code rather than the value of a variable.
So it depends on the context, but you can essentially change the casting of a pointer. So for example, if you have a pointer to an integer and you want to change the cast to a long integer, or you want to change it to a float, instead of actually having to do that coercion in the code and recompiling the code, you can apply that coercion interactively in the debugger. So in all fairness, not something you do as much in HPC numerical oriented code as you would in more systems oriented stuff. In all fairness, much more typically in HPC codes, you would be interested in changing the actual value, not the type that you're casting to.
Okay, thanks.
Okay, so there's a couple ways to do offline debugging. You can submit your job in the batch system, say offline, and give it arguments of what you want for breakpoints. A simpler way is to set up a session file where you specify what you want and then add the session file. So I'll talk a little bit about each. And also in the follow-up notes that I included in the slides, I have a couple blogs where I go into quite a bit of depth on offline debugging. There's really a lot of capability, and it's one of my kind of favorite recent features, so to speak, in that I think I've seen more customer success stories of really challenging problems solved with offline debugging than any other capability, especially at scale. We've had several cases where sites have a very large scale problem that's very difficult to debug interactively. It's hard to get a reservation or many opportunities, and offline debugging is a great way to track that down. So let's go through creating a session file. So just going to clean up some of my existing definitions. Okay, let's set a breakpoint, then a trace point similar to what we had. Maybe just output one of these values. And maybe output every other iteration. It's just going into a file. And leave the watch point that we had. Okay, so at this point, I'm just using the user interface to set up and define that session file. I'm not really running in earnest, so we could actually run this on our login node and not even go through the batch system. And then we select File, Save Session. This is just an XML file that we're going to give to the run. Okay, so now The operational mode for this on your system would then be to go to your existing batch file on the login node and prefix the app run, MPI run type of operation with DDT-offline, then the name of the session file. So in general, I recommend using memory debugging whenever you're in debugging mode, even if that's not what you're looking for, and that catching memory bugs in particular sooner than later is a big advantage. But especially in offline mode, the overhead is very small, so recommend always doing that. So balanced is essentially close to the set of flags that I showed you in the interactive dialog. And then the actual scale of your program. Now, you do not need to create your session file at the same scale, so to speak, as you do when you run it. So the typical workflow is you're going to bring up and create your session file with just a couple processes. And then when you go to submit it, you can run the job at a much larger scale where the problem occurs. Okay, so then we submit our job. Submit the job as you normally would. It's going to run and create .air, .out files as your system normally does. And then in addition, by default, it's going to create an HTML file. And we'll go through what that HTML file looks like. We can also create it as a CSV file. And in the follow-up materials I have in the slides, I go into a lot of detail that and the trade-offs. So you can easily create a lot of information with this process. It's a great way when you're looking for a bug and you don't have a really focused pattern yet of where the problem might be. Put in a lot of instrumentation and you can gather a lot of information very quickly to help refine your search. The one caveat that is, especially in HTML mode, you can create a lot of output data. So I recommend once you start to focus your search and you're putting in a lot of instrumentation, use the CSV approach because it's a little easier to post-process with sed, grep, awk type tools and won't overwhelm the system quite so much. Okay, so it picked a name for me there. Let's open that up. All right, without my mouse today, so feeling a little clumsy. Okay, so here's the HTML file that it just generated. Very similar to the logbook within the user interface. Shows the time of the executable build, the variables that are being set, and then we can scroll down. We can see at the breakpoints that we set in main, it dumps the entire state of the program, and within the HTML we can drill down and it presents the data in a very similar form as it did within the user interface using the sparkline metaphors and the stacks view as we have within the user interface. Just one thing I want to highlight is breakpoint is a kind of an unfortunate name in offline mode in that none of the breakpoint watch points settings actually halt execution. When we're in offline mode, instead of actually halting execution as we do in the user interface, we just dump the state of the program to this file. All right, continuing down, we see the state when we hit the watch point. So information, so we can see even for this simple, rather short program, a very easy way to gather a lot of information about the execution state of the program. All right, some point here, we just get my trace points. There they go. Okay, and then the trace points, once again, similar to the user interface where we have the sparklines to see the shape of the variable across the processes, the actual range of the process for X across all the processes. We had on memory debugging, so a little bit of information about memory usage. It's really not a memory leak per se in this program, but we can click on elements of that bar chart to drill down to see how memory is being allocated within that selection. So very useful way for if you do have a memory leak at scale or in a large run, running in an offline mode is really powerful way to track that down. And then the actual output that would be in your .out type file in your batch system is also included. So really like to highlight offline debugging. Really encourage you to check out some of the blogs I included in the follow-up materials. It really is one of, I think, the most important features for really difficult bugs, non-deterministic bugs that are very random, and especially at sites like yours that do large-scale HPC. My background is mainly I work with US sites. That's fairly new for me. I've been working with European sites, so don't know a lot of your history, but at the US labs, large US DoD, DOE type sites, this is one of the most important capabilities for large HPC related problems. And that was kind of a whirlwind up, but there's a lot involved. Once again, especially the stuff related to generating output in CSV files and how to post-process that, I really encourage. So that's the bulk of it, and it looks like I'm pretty close to the hour, but it looks like we have a few minutes if there are any questions.
If there, okay, so there is one question. How does one use DDT with Slurm? So I guess you just added to the bash file, right? You were saying.
Yes, so I apologize, I'm not familiar with your site setup, but at a high level, there's two steps. You install the client on your local machine. You can store it for Windows, Macintosh, or Linux. You install the client. There's some configuration you have to do with the clients, and I'm pretty sure that that's for your site. There's some reference pages of how that is done. Once the client is installed, you log into the cluster, you go to your existing job submission file, and you prefix the existing app run or MPI run with DDT space -- session. Once again, I apologize, I don't know your site very well, but if you contact one of your site administrators, I'm sure they can give you. Great, there we go. The details on how to do that.
Yeah, so because we're kind of short on time, if there are any other questions, feel free to raise a hand and speak up.
Yeah, absolutely. And my email is in the slides that that I shared. Feel free to reach out to me directly. I would encourage that you also include one of your site people, and that I don't know your machine very well, but in terms of using the tools, do feel free to reach out to me directly. Great. Well, if not, I guess that's kind of it. And once again, next week we will be talking about our performance tools, performance reports, and map. Also, covering those is a little bit less ground to cover. So if you do have questions, we can probably start out with those during next week's session, as going over map and performance reports probably will require a little less time.
Okay, great. Thank you very much, Beau. I think that was very helpful, and I will definitely be trying some of this stuff out.
Great, great. Good to hear that. All right. Well, see you next week then.